We're going to start talking about problems that are a little bit more complicated than the ones we've been doing. What's going to happen is there are going to be two or more types of motion happening in the problem. You have to keep them separate. So here's an example. We have a runner running a 100-meter dash, accelerating for the first part, but then running at constant speed for the rest of it. So if I was to sketch that, it would look something like this. Here's the whole 100 meters. Okay, my information is telling me that he starts from rest, from 0 to 0. And for the first 80 meters, his acceleration is 0.9 meters per second squared. For the rest of it, which is 20 meters, I know that his acceleration is 0 because he's going at constant speed. So that's okay. Now, I have to split it up into the accelerating part and the constant speed part. So for the accelerating part, my givens are v0 is 0, delta x is 80 meters, and the acceleration is 0.9 meters per second squared, and then I can use that to find the v and the t, right? How long it takes to cover the 80 meters, and its velocity right here at the end of the 80 meters. I'm going to start with the velocity. I'll use v squared is v0 squared plus 2a delta x. I get v squared equals 0 squared plus 2 times 0.9 times 80. But if I solve that, I'll end up with a velocity of 12 meters per second. So right here, I just found that his velocity is 12. Then I can use this equation to find time. So 12, 0 plus 0.9 t. And if I solve that, I'll get a time of 13.3 seconds. So that was the time for the first part of the race. Now, I'm going to do the constant speed part. There's a couple ways to do it, but if I want to use the same method, I can say the acceleration for that part is 0. The initial speed for that part is 12. Because the ending speed for the first part of the race is the beginning speed for the second part. And then I know that the distance for that part is 20 meters. And then I'm going to look for the time because that's my goal. It's not how long it takes to run the entire race. So now I'll use this equation. This simplifies a lot because the acceleration is 0. I don't have to worry about this part. And I just get delta x is 20 equals 12 times t. When I do that, I'll get a time of 1.6 repeating for the second part. So now to get the total time, I can just add those. Plus 1.6 repeating. And that's going to give me 15 seconds for the total race. Here's another example on the next page. Okay, in this case, I have a car traveling at constant speed. It's going to pass a police officer. At that moment, the police officer starts to press, accelerating at 3 until he has got the car. How far from the starting point will the police officer catch the car? If I was to graph it, it might look something like this. X, t. The car is going at a constant speed like this. The police officer starts to press, speeds up until he catches him. So again, I have to separate out what I know about each one. So for the car, I know that his acceleration is 0. His initial velocity is 30 meters per second. Okay. And that's all I have for him. And for the police officer, all right, his acceleration is 3. And his initial velocity is 0. Now, there's a number of ways to do this one. What I'm going to do is I'll know that the police officers caught him when they have gone the same distance. So if I look at this equation, delta x is v0t plus 1 half squared. With a car, I'll get delta x equals 30 times t, and then there's no acceleration, so I don't have to worry about that part. For the police officer, I'll plug in the same equation. So delta x equals, this time the v0 is 0, so I don't have to worry about that part. And I'll get 1/2 times 3 times t squared. So this gives me delta x is 1.5 t squared. Now, to catch them, these two have to match. So delta x for the car equals delta x for the police officer. So 30t equals 1.5 t squared. I could divide both sides by t. That'll simplify this. I'll get 30 is 1.5t. Then divide by 1.5, and I'll get t is 20 seconds. Now, I can find the velocity of the police officer if I want at that point. And his velocity is going to be 60 meters per second. I can also find his position. Up here I have the equation equals 1.5 t squared. So if I plug that in, I get 1.5 times 20 squared, and that's 600 meters. So now, I put this graphic down here because we can do x versus t and v versus t graphs just to see what happens. All right. So the police officer in 20 seconds goes 600. So how should I scale this? Let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So there's 10. There's 20 seconds. I can do the same thing over here. There's 10, and there's 20. And then his final position is 600. So I'm just going to throw 1, 2, 3, 4, 5, 6, get this 600 up here at the top. The police officer starts at 0, ends at 600, and he's speeding up the whole way. So I'm going to have to connect those with the graph with an increasing slope showing that he's speeding up. So that's the police officer. Okay? The car, on the other hand, is going at constant speed. He starts at 0 and ends at 600. They end up in the same spot. So I can draw his graph like this. Now, for the velocity, the police officer starts with a velocity of 0, and after 20 seconds has a velocity of 60. So let me scale this out. 10, 20, 30, 40, 50, 60. So he starts at 0 and ends at 20. So he's speeding up the full way, so his velocity is going to look like that. So we'll label that one the police officer. The car has a constant speed of 30, so that means he stays at 30 the whole time. So that would be a graph for both their motions. The kind of interesting thing, or something you may notice about this, is displacement is the area under the graph. And if I look at these two graphs, they have the same area. Okay? The car has this bigger rectangle here, whereas the police officer has this triangle. But if I took this part off this triangle, I could put it over here, and you would end up with the same area. So if you have a more complicated problem, either two different objects moving, write down the givens for each of the two objects. Or, for the previous problem, it was one object doing two different types of motion at two different times. You have to write down the variables for each part of the motion individually.